The observable universe is 93 billion light-years across. That number is large enough that most people hear it, nod, and file it somewhere in the mental folder, labeled very big things I cannot actually comprehend. 93 billion light-years, fine, very large. Moving on. But here is the thing that never gets said clearly enough in the moment after that number is presented. The observable universe is not the universe. It is the part of the universe we can see, the part from which light has had time to reach us in the 13.8 billion years since the Big Bang. It is a sphere of visibility centered on us, bounded by the distance light can travel in the age of the universe, and it represents a fraction of the total universe whose size we do not know. We do not know if it is a large fraction or a small one. We do not know if the total universe is 10 times the observable universe, or 1,000 times, or 1,000,000,000,000 times. We do not even know with certainty whether it has an edge at all. And there is evidence, not proof in the mathematical sense, but the kind of convergent evidence from multiple independent lines of observation that physicists treat as something very close to proof, that the total universe is vastly, incomprehensibly, perhaps infinitely larger than the 93 billion light-year bubble we can see. The word infinite is doing real work in this video. Not infinite in the casual sense of very, very large. Infinite in the literal mathematical sense, without bound, without edge, extending forever in every direction, containing an unlimited amount of matter and space, and, if the implications are followed all the way out, containing somewhere exact copies of everything that has ever existed, including you. This last part is not metaphor. It is a straightforward consequence of infinite space combined with finite configurations of matter. We will get there. But before we get there, we need to understand what the evidence actually is, why it points toward infinite space rather than finite, and why the word terrifying in this video's title is not clickbait. The terrifying part is not that the universe is large. The terrifying part is what a literally infinite universe logically requires to be true. One more thing before we start. Some people hearing the argument in this video find it liberating rather than terrifying. If there are infinite copies of you, then in some sense, every version of every choice you might have made exists somewhere in the universe. Every path not taken is taken infinitely many times by a physical version of you. Whether this is terrifying or comforting depends entirely on your prior beliefs about what makes your existence meaningful. We will return to that question at the end. We start with flatness. Chapter 1, The Shape of Everything. What the CMB told us. In the year 2003, a satellite called WMAP, the Wilkinson Microwave Anisotropy Probe, produced the most detailed map of the cosmic microwave background that had ever been made. The cosmic microwave background is the oldest light in the universe. When the universe was about 380,000 years old, still unimaginably young, a fraction of a percent of its current age, it was hot and dense enough that photons could not travel freely. The universe was an opaque plasma, a fog of charged particles so tightly packed and energetic that any photon emitted was immediately absorbed. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. When that happened, the fog lifted. The photons that had been trapped in the plasma were suddenly free to travel. They have been traveling ever since for 13.8 billion years, cooling and redshifting as the universe expanded. Until today, they constitute a faint microwave background, filling the entire sky at a temperature of 2.725 Kelvin above absolute zero, barely above the coldest temperature the universe permits. That background radiation is not perfectly uniform. It has tiny temperature variations, fluctuations of about 1 part in 100,000, that encode the initial density perturbations in the early universe, the seeds from which all the galaxy clusters and cosmic structure we see today eventually grew. The pattern of these fluctuations, their angular scale, their amplitude, the correlations between them across the sky, contains extraordinary amounts of cosmological information. One of the things it contains is a measurement of the curvature of space. Here is why that works. The early universe was full of sound waves. Before the photons were released, the plasma was an acoustic medium, and pressure waves propagated through it the way sound waves propagate through air. These acoustic oscillations produced a characteristic pattern in the density fluctuations. A preferred length scale, the distance a sound wave could travel in the roughly 380,000 years between the Big Bang and recombination. This preferred scale, called the sound horizon, is imprinted in the CMB as a preferred angular separation between the temperature fluctuations. The angular size of the sound horizon as seen in the CMB depends on two things: the physical size of the sound horizon, which can be calculated from the physics of the early universe, and the geometry of the space the light has traveled through to reach us. If space is flat, Euclidean, extending in straight lines, then the angular size is the specific predictable value. If space is positively curved, like the surface of a sphere, but in 3 dimensions, then the light curves toward us, and the sound horizon appears larger on the sky. If space is negatively curved, like a saddle surface, but in 3 dimensions, the light diverges and the sound horizon appears smaller. The WMAP measurement, refined substantially by the Planck satellite mission in 2013 and again in 2018, found that the angular size of the sound horizon is consistent with flat space to a precision of about 0.4%. The universe, to the best measurement we have ever made, is geometrically flat. The reliability of this measurement is worth dwelling on, because it is the foundation of everything that follows. The CMB curvature measurement is not a single data point from a single instrument using a single method. It is a convergent result from multiple independent datasets, WMAP, Planck, and prior ground-based and balloon-borne experiments using different detectors, different analysis pipelines, different teams. They all get the same answer. Moreover, the CMB flatness measurement is cross-checked by entirely independent cosmological observations. Baryon acoustic oscillations, the same sound horizon imprinted in the CMB, but now visible as a preferred clustering scale in the distribution of galaxies, give a consistent flatness measurement using different data and different techniques. Weak gravitational lensing surveys, which measure the curvature of space by the distortion of galaxy shapes, also give consistent results. The flatness of the universe is not an artifact of a single measurement or a single method. It is a result that has been confirmed across every cosmological data set we have, at every epoch, using every available technique. This matters because the chain of reasoning from flat CMB to infinite universe is only as strong as the flatness measurement itself. If the measurement were fragile, if it rested on a single data set with known systematic uncertainties, the infinite universe conclusion would be correspondingly uncertain. But the flatness result is among the most robust in all of cosmology. It has been tested harder than almost any other cosmological parameter, and it keeps coming out flat. This is not what cosmologists in 1970 expected to find. The flatness was a surprise, not because a flat universe was thought impossible, but because the probability of landing on exactly the critical density by chance seemed negligibly small. The precision of the flatness, once it was measured, immediately suggested that something was forcing the universe to be flat. That something, as the next chapter explains, is what solves several other cosmological puzzles simultaneously. This is a statement with enormous consequences, and it is the first line of evidence for an infinite universe. Here is why. A flat universe is consistent with two possibilities. It is infinite, extending flat forever in all directions, or it is finite, but with a topology that loops back on itself, a kind of flat but closed space, like the surface of a torus, where if you travel far enough in one direction, you eventually return to your starting point from the other side. Both of these are consistent with zero curvature at any local measurement. A positively curved universe, like the surface of a sphere, is necessarily finite. A sphere has a finite surface area. A three-dimensional space with positive curvature curves back on itself and has finite volume. If the universe had positive curvature, it would be finite, and its size would be determined by the radius of curvature. The WMAP and Planck measurements rule out positive curvature at the level of their precision. Not absolutely, there is always measurement error, but to within 0.4%. The universe is flat or indistinguishably close to flat, and if it is flat, it is either infinite or so large that its topology loops back on itself at a scale so enormous that the looping is invisible within the observable horizon. If the topology looping is real, if the universe is a torus, then there should be a signature. Repeated patterns in the CMB, where the same structure appears in multiple locations corresponding to the same region of space, viewed from different copies through the periodic topology. Searches for this signature in the WMAP and Planck data have found no evidence of it. The universe does not appear to repeat within the observable horizon. This does not prove the universe is infinite. The absence of detected repetition could simply mean that the topology scale is larger than the observable horizon, that the universe loops back, but so far away that we cannot see the repetition. This is consistent with both a very large finite universe and an infinite one. But the flatness measurement, combined with the absence of topological repetition, and combined with the theoretical understanding of why the universe should be flat to begin with, which we will get to shortly, makes a flat, infinite universe by far the simplest and most natural interpretation of the data. It is not proven, but it is the working assumption of virtually every cosmologist, built into the standard model of cosmology, consistent with every observation made, and supported by theoretical reasoning that goes much deeper than the CMB measurement alone. The flatness of the universe is the first reason to believe it, is infinite. And it raises an immediate question. Why is it flat? Why, out of all possible curvatures, positive, negative, flat, does the universe happen to have exactly the one that corresponds to zero? The answer to that question is the second reason, and it involves the most dramatic event in the universe's history. Chapter 2: Inflation, the engine that made the universe. Flat. In the standard Big Bang model, without any additional physics, flatness is a problem. It is called the flatness problem, and it was identified in the 1970s as one of the deep puzzles of cosmology. Here is the issue. The universe's geometry, its curvature, changes over time as the universe expands. In a universe dominated by matter or radiation, a small deviation from flatness in the early universe grows with time. The universe becomes progressively more curved, not less. A universe that is slightly positively curved becomes more positively curved. A universe that is slightly negatively curved becomes more negatively curved. Flat space is an unstable equilibrium. Any small departure from flatness compounds over time. This means that if the universe is close to flat today, it must have been extraordinarily close to flat in the early universe. To be as flat as we measure today, to within 0.4%, the universe at 1 second old must have been flat to within about 1 part in 10 to the 16th power. At the Planck time, the earliest moment accessible to standard physics, the universe must have been flat to within about 1 part in 10 to the power of 60. 1 part in 10 to the power of 60. The number 1 followed by 60 zeros in the denominator. The universe in its very first moments had to be calibrated to a precision that has no analog in any human experience of fine-tuning. Why? There is nothing in the basic Big Bang model that would require this. It appears in the standard model, without additional physics, to be an extraordinary coincidence, a cosmic accident of almost inconceivable precision. The solution proposed in 1980 by Alan Guth and developed further by Andrei Linde, Alexei Starobinsky, and others is called inflation. Inflation is a period of exponentially rapid expansion that occurred in the very early universe, earlier than 10 to the power of minus 32 seconds after the Big Bang, possibly much earlier. During inflation, the universe expanded by a factor of at least 10 to the 26th power, and possibly by a vastly larger factor in an extraordinarily short time, driven by the energy of a scalar field called the inflaton. Inflation solves the flatness problem in a specific and elegant way. Imagine the surface of a sphere. If you zoom into a small enough region, it looks flat. The curvature of the surface is there, but at fine enough scales it is invisible. The surface looks Euclidean. Now imagine inflating that sphere to astronomical size, expanding it by a factor of 10 to the power of 26 or more. Any region that was initially the size of a proton is now cosmological in size, and the curvature of that region has been diluted to an imperceptible level. The original curvature is still there in principle, but the expansion has stretched it out to a scale so large that it is undetectable within any accessible region. This is what inflation does to the universe's curvature. Whatever curvature the universe had before inflation, the inflationary expansion diluted it. A highly curved early universe after inflation appears flat to any observer within the expanded region. because the scale of the curvature is now many orders of magnitude larger than the observable horizon. The universe we observe is not specially flat because of a coincidence. It is flat because inflation made it flat, by stretching any curvature to scales far beyond what we can measure. And here is the connection to the infinite universe. If inflation occurred, it produced a region of space that is flat to extraordinary precision. The observable universe, the 93 billion light-year sphere we can see, is a tiny fraction of the region produced by inflation. Current inflationary models predict that the total region produced by inflation is at minimum 10 to the power of 23 times larger than the observable universe. More aggressive models predict factors of 10 to the power of 10 to the power of 20 or larger. In most inflationary models, the total volume of space produced by the inflationary expansion is not merely very large, but is genuinely infinite. This is because most inflationary models involve what is called eternal inflation. Once inflation begins, in most models, it does not stop everywhere at once. It stops locally in regions that exit the inflationary phase and evolve into hot Big Bang universes, like ours. But in other regions, inflation continues. And because the inflationary expansion is exponential, the volume of the still inflating regions grows faster than the volume of the regions that have stopped inflating. The total volume of the still inflating space increases without bound. Inflation, once started, never fully ends. It continues forever, producing bubble after bubble of post-inflationary space-time, each one potentially an entire universe like ours, in an eternal, self-replicating process. The concept of eternal inflation, developed primarily by André Linde in the 1980s and further extended by Alan Guth, Alexei Starobinsky, and others, implies that what we call the universe, the observable universe, our Big Bang, the 93 billion light-year sphere, is a single bubble in an infinite, eternally inflating space. The total space-time is not 93 billion light-years. It is not a trillion light-years. It is not any finite number. It is infinite. To make eternal inflation concrete, imagine a vast, expanding space in which inflation is occurring everywhere. In this space, the inflaton field has a quantum mechanical character. It fluctuates, and in most regions, the fluctuations keep it at a high energy value where inflation continues. But occasionally, in small regions, the field fluctuates to a lower energy and inflation ends. When inflation ends in a region, the energy stored in the inflaton field is released as a hot Big Bang, a reheating event that fills the region with matter and radiation, setting the stage for the evolution of a universe like ours. The region then continues to expand, eventually becoming what we would call a universe. Meanwhile, in the surrounding still inflating space, new such regions are forming, each one a new Big Bang, each one a potentially different universe. The rate of bubble formation is finite, but the volume of the still inflating space grows exponentially. In any finite time, infinitely many bubbles have not yet formed, and the inflating space has already expanded to accommodate infinitely many more. The process is self-sustaining. Inflation, once started, never ends globally. It ends locally in the bubbles we call universes. But the whole continues inflating and expanding and producing new universes forever. This is a theoretical framework, not a direct observation. But the theory is supported by the observation of flatness, by the patterns in the CMB that are consistent with inflationary predictions in extraordinary detail, and by the resolution of other cosmological puzzles, the horizon problem, the monopole problem, that have no other clean solution. Inflation is not confirmed, but it is, by a significant margin, the best available explanation for why the universe is flat, smooth, and the way it is. And if inflation happened, an infinite universe is, in most models, the expected outcome. Chapter 3: The Flatness Number. What the Planck satellite actually found. It is worth spending a moment with the actual number, because the precision of the measurement is itself remarkable, and because the details of what was measured and what they imply are richer than the summary suggests. The Planck satellite, launched by the European Space Agency in 2009, measured the cosmic microwave background with a sensitivity and angular resolution that surpassed all previous instruments. Its final cosmological results, published in 2018, measured the total energy density of the universe as a multiple of the critical density, the specific density at which the universe is exactly flat. This ratio is denoted omega. A flat universe has omega equals 1. A positively curved universe has omega greater than 1. A negatively curved universe has omega less than 1. Planck's measurement: omega equals 1.007 plus or minus 0.0019. The universe's total energy density is 100.07% of the critical density, with an uncertainty of 0.19 percentage points. Within the measurement error, it is consistent with exactly flat. The deviation from flatness is not measurable. The universe is flat. To understand what this means, consider what omega consists of. The total energy density of the universe is the sum of several components. Ordinary matter, baryons, the protons and neutrons and electrons that make up everything you can touch, contributes about 5% of the critical density. Dark matter, the gravitationally detected, non-luminous, unknown substance that holds galaxies together, contributes about 27%. Dark energy, the unknown substance or property of space-time that is driving the accelerating expansion of the universe, contributes about 68%. These three components together sum to approximately 100% of the critical density, giving a flat universe. The extraordinary precision of the flatness measurement, not just the central value, but the fact that three completely independent components of the universe's energy budget sum to precisely the critical density, is itself a powerful constraint on cosmological models. In a random universe, there is no reason why the sum of matter, and dark energy should equal exactly the critical density. There is no a priori reason for these three components to balance so precisely. In the standard inflationary cosmology, this balance is not a coincidence. It is a prediction. Inflation drives the total density to the critical density and keeps it there. The Planck measurement is precisely what inflation predicts. The measurement has one subtlety worth noting. The central value of omega equals 1.0. 0.007 is technically slightly above 1, which would imply a very slightly positively curved universe. This is within the measurement error. It is not a statistically significant departure from flat, but it has generated some discussion. a handful of papers have argued that the data actually slightly prefer a closed, positively curved universe, which would be finite. These papers use different statistical treatments of the Planck data and come to the conclusion that a very gently closed universe is marginally preferred over an exactly flat one. This interpretation is not mainstream. The majority of cosmologists regard the omega equals 1.0007 value as consistent with flat to within measurement precision and interpret it as supporting the standard flat, infinite model. But the minority view is not scientifically indefensible, and it illustrates an important point. The inference from flat CMB to infinite universe is very well supported, but it is an inference, not a proof. The universe could be very slightly closed, very large and finite, but finite, and the current data could not definitively rule that out. What would a very slightly closed universe look like? If omega were, say, 1.0002 rather than exactly 1, a departure from flat of 2 parts in 10,000, the universe's positive curvature would mean it closed back on itself at a distance enormously larger than the observable horizon. The circumference of such a universe would be at minimum several hundred times the diameter of the observable universe, hundreds of billions of light years, perhaps thousands of times. The universe would be finite, but so large that its finiteness would be, for all practical purposes, irrelevant. Any structure beyond the observable horizon would be fundamentally inaccessible. But fundamentally inaccessible and does not exist are different things, and the implications of the two possibilities, finite but enormous or truly infinite, are qualitatively different in ways that go far beyond the practical. And the implications of the truly infinite case, which is what most of the data supports, and which is the standard assumption of modern cosmology, are what make this video's title honest rather than hyperbolic. Chapter 4: The Horizon Problem. Why the universe is so smooth. The flatness problem is not the only thing inflation explains. There is a second problem with the standard Big Bang model, called the horizon problem. That is equally severe, and that provides an independent line of evidence for inflation, and through inflation, for the vast or infinite extent of the universe. The cosmic microwave background, as measured by WMAP and Planck, is extraordinarily uniform. The temperature, variations across the sky are only about 1 part in 100,000. In every direction you point a telescope, the CMB has the same temperature to extraordinary precision, 2.725 Kelvin. This uniformity is, on the face of it, unsurprising. It sounds like the universe should be uniform if it started in the same Big Bang. But look more carefully, and the uniformity becomes a profound puzzle. The uniformity of the CMB means that regions of the early universe that are now in opposite directions on the sky had the same temperature, to 1 part in 100,000, when the CMB was emitted. But here is the problem. Those regions were not in causal contact when the CMB was emitted. The distance between them at the time the CMB was released was larger than the distance light could have traveled since the Big Bang. They had never been able to exchange information. They could not have communicated, could not have thermalized, could not have agreed on a common temperature through any ordinary physical process. This is the horizon problem. In the standard Big Bang model without inflation, the observable universe at the time of CMB emission consisted of roughly 40,000 causally disconnected regions that had never been in causal contact with each other. Yet all 40,000 of them had the same temperature. Without inflation, this would require an extraordinary coincidence. 40,000 separate regions of the universe, never having interacted, all independently settling at the same temperature to 1 part in 100,000. Inflation solves the horizon problem in the same way it solves the flatness problem, by stretching. Before inflation, the entire observable universe was a tiny, causally connected region, small enough that all of it had time to thermalize and reach a common temperature. The inflationary expansion then took this tiny, uniform region and stretched it by a factor of at least 10 to the 26th power, producing a vast region of uniform space. The 40,000 causally disconnected regions of the post-inflationary universe were not independently uniform. They were all part of the same causally connected region before inflation, and inflation stretched that region to cosmic scales. This is the second major reason to believe inflation happened. And if inflation happened, the universe is not just larger than what we can see. It is vast beyond any meaningful comprehension, and quite possibly infinite. But there is a third line of evidence, and it is the most direct. It comes not from the overall uniformity or geometry of the CMB, but from the specific pattern of fluctuations within it. Chapter 5: The Spectrum of Fluctuations. Inflation's Fingerprint. The tiny temperature variations in the CMB, 1 part in 100,000, are not random noise. They have a specific statistical structure, a specific pattern of fluctuations across different angular scales that can be measured precisely and compared to theoretical predictions. In the inflationary picture, the fluctuations in the CMB were generated during inflation itself. During the inflationary expansion, quantum fluctuations in the inflaton field, tiny random variations generated by the inherent uncertainty of quantum mechanics, were stretched by the inflationary expansion to macroscopic scales. What began as a quantum mechanical jitter at subatomic scales was blown up to cosmic sizes, frozen in by the inflationary expansion, and imprinted as density fluctuations in the post-inflationary universe. These density fluctuations then evolved under gravity, forming the sound waves in the early plasma that left their imprint in the CMB, and eventually collapsing under their own gravity to form the galaxies, clusters, and cosmic web we observe today. The specific prediction of inflation for the CMB fluctuation spectrum is a nearly scale-invariant spectrum. Fluctuations of roughly the same amplitude on all scales, with a slight preference for more power on large scales, characterized by a spectral index close to but slightly less than 1. The spectral index is conventionally denoted NS, and pure scale invariance corresponds to NS equals 1. Planck's measurement of the spectral index, NS equals 0.9649 plus or minus 0.0042. The spectral index is slightly less than 1, exactly as inflation predicts. The deviation from pure scale invariance is small but measurable, and its value constrains specific classes of inflationary models. This measurement, combined with the flatness measurement and the uniformity of the CMB, constitutes a 3-part test of inflationary theory that the data passes with remarkable precision. the spectral index measurement also does something more specific. It begins to narrow down which inflationary models are correct, and therefore which predictions about the universe's extent are most reliable. Different inflationary models, different potentials for the inflaton field, predict slightly different values of on-S. The simplest single-field inflationary models, particularly the so-called plateau models like Starobinsky inflation and similar variants, predict NS in the range 0.960 to 0.967 for observable quantities consistent with the number of e-folds of inflation accessible to our observations. The Planck measurement of 0.9649 falls squarely in this range. More strikingly, the Planck data also placed constraints on the tensor-to-scalar ratio, the ratio of gravitational wave fluctuations to density fluctuations generated during inflation. Gravitational waves produced during inflation leave a specific imprint on the CMB in the form of B-mode polarization patterns. Planck found no detection of primordial B-modes, placing an upper limit on the tensor-to-scalar ratio of RR less than 0.064. This rules out a large class of large field inflation models where the inflaton field moved over a large range of values during inflation, and favors small field and plateau models. The significance of this for the infinite universe argument. The plateau models that best fit the data are precisely the models that most naturally produce eternal inflation. The flat potential of a plateau model is exactly the configuration where quantum fluctuations in the inflaton field are most likely to keep some regions in the inflating phase while others exit, the prerequisite for eternal inflation. The Planck constraints on inflation are not just confirming that inflation happened. They are pointing toward the specific classes of inflationary models that most robustly predict an eternal, infinite inflationary background. What the spectral index measurement means for the infinite universe argument is this. The quantum fluctuations that seeded the CMB were stretched across the entire observable universe during inflation. The same inflationary process that stretched those fluctuations to cosmic scale also stretched space itself to scales far beyond the observable horizon. If the inflationary stretching produced the observable universe, it produced the same stretching everywhere to arbitrarily large distances. The same physics that explains the CMB fluctuation spectrum requires that the universe extends, flat and uniform, far beyond what we can see. With the same small amplitude density fluctuations, the same scale invariant spectrum, filling the space beyond our horizon as far as it extends. If the universe is infinite and flat, and filled with a nearly scale invariant spectrum of density fluctuations, extending everywhere, then those fluctuations have been evolving for 13.8 billion years everywhere, not just in our patch. Everywhere, matter has been collapsing under gravity, forming stars and galaxies, producing the same structures we observe locally. The universe beyond the horizon is not empty, not strange, not fundamentally different from our local region. It is more of the same. Galaxies, clusters, cosmic filaments, voids, the same structures statistically as we observe here. This leads directly to one of the most unsettling implications of infinite cosmology, and it is time to confront it directly. Chapter 6: The Level 1 Multiverse. Copies of you right now. The argument is not complicated. It follows from three premises, each of which is well supported by evidence. Premise 1. The universe is spatially infinite, or at minimum so large that its total volume is not meaningfully bounded for the purposes of this argument. Premise 2. Matter in the universe is distributed randomly, with quantum fluctuations providing the seeds for the specific configurations of matter we observe. Premise 3. The number of possible quantum states for any finite region of space, any region with a finite volume and a finite energy, is finite, not infinite. These three premises together imply something that takes a moment to absorb. If the universe is infinite, it contains an infinite amount of space. Each region of space has a finite number of possible quantum states. Therefore, by elementary combinatorics, every possible quantum state of every possible finite region must be realized somewhere in the infinite universe, and must be realized not once but infinitely many times, including the quantum state of the observable universe, including the quantum state of the room you're in right now, including the quantum state of your brain, with its specific configuration of neurons, memories, thoughts, and whatever sense of self you currently experience. In an infinite universe, there are infinitely many regions of space that are, right now, quantum mechanically identical to the observable universe. Not similar, not analogous, but identical. Atom for atom, quantum state for quantum state, right down to the specific configuration of your brain in the specific moment of reading or hearing this sentence. These copies are real. They are physical. They are made of matter, operating under the same laws of physics, experiencing the same experiences. They are not philosophical abstractions or thought experiments. They are physical regions of the universe currently existing, separated from us by distances so large that no light from us will ever reach them, but subject to the same physics, the same quantum mechanics, the same history. This is the level 1 multiverse in physicist Max Tegmark's classification, not a multiverse in the sense of different physical laws or different dimensions, but a multiverse of causally disconnected regions of a single, flat, infinite space, each one a repetition of every possible configuration of matter. The concept was discussed seriously long before Tegmark named it, by cosmologists including Alexander Vilenkin and Alan Guth. It is a direct, unavoidable consequence of an infinite universe combined with quantum mechanics. How far away are the nearest copies? The calculation is not difficult in principle, though the numbers are extraordinary in practice. The observable universe contains roughly 10 to the power of 80 protons. That is, the rough estimate of the number of protons in the observable universe. The number of possible quantum states for a region the size of the observable universe is bounded by the Bekenstein bound, the maximum amount of information that can be contained in a given volume, which gives something in the range of 10 to the power of 10 to the power of 123 possible states. This is the number of distinct configurations a region the size of the observable universe can be in. By the birthday paradox of combinatorics, if you have an infinite number of observable universe-sized regions, the expected distance to the nearest region in the same state as ours is approximately 10 to the power of 10 to the power of 123 meters, a number so absurdly large that it does not fit comfortably into any notation. It is not a billion light years. It is not a Google light years. It is 10 raised to the power of 123 meters, where 123 is itself a number so large that writing it out in decimal would require more digits than there are atoms in the Chuseau-Duwon observable universe. This distance is physically real. It is not a metaphor. In an infinite universe, there is a region at approximately that distance that is, right now, a quantum mechanical copy of the observable universe. There is a copy of you, reading or watching this, having the same thought you are having, in a galaxy that is indistinguishable from the Milky Way, around a star indistinguishable from the Sun, on a planet indistinguishable from Earth. The word terrifying in this video's title is specifically about this. Not the size is just a number, but the implication that you're not unique. Before you dismiss this as abstract, consider it from a slightly different angle. You have a history, a specific sequence of events that led to who you are. The parents you were born to, the childhood you experienced, the choices you made, the person you became. These events feel singular to you. They feel like your story, not a generic story. The specificity of your experience, the precise texture of your memories, the exact character of your relationships, the particular way you think, feels like something that belongs uniquely to you. In an infinite universe, every one of those specific events is reproduced. The childhood memory that feels most distinctly yours, the one you have never told anyone, the one that feels like it belongs only to you, is being experienced right now, identically, by an infinite number of beings who are physically indistinguishable from you. The choice you feel most proud of or most ashamed of, that you made alone in a moment when nobody was watching, it is being made, identically, by an infinite number of copies. Your sense of being a singular, unrepeated individual is, in an infinite universe, an illusion, not a comforting illusion, a physical one, a consequence of the finite speed of light preventing you from knowing about your copies, not a consequence of actually being unique. This is not a new observation. The philosopher Derek Parfit spent decades working through the implications of personal identity under conditions of physical duplication. What identity means when there can be exact copies of a person, and whether the self is the thing that matters, or whether what matters survives copying. Parfit's conclusion, roughly, was that personal identity in the strict sense does not matter as much as people think it does. That what matters is psychological continuity and connectedness, not numerical identity. An infinite universe makes Parfit's thought experiments not hypothetical but actual. The word terrifying in this video's title is specifically about this. Not the size is just a number, but the implication that you are not unique. Not in the philosophical sense. Everyone knows that every individual is unique in some meaningful sense. But in the physical sense, there is no physical fact about you, no quantum configuration of your body and brain that is not realized an infinite number of times elsewhere in an infinite universe. Your specific history, your specific memories, your specific experience of reading this sentence, they are happening right now in an infinite number of distinct locations in the universe, all experiencing that same moment, none of them able to communicate with any of the others. This is not science fiction. It is the straightforward implication of the flatness of the universe, the theory of inflation, and quantum mechanics. It follows from the data. It is what the CMB is, in a sense, telling us. Chapter 7: Dark Energy and the Expanding Universe. Why the evidence keeps growing. If the CMB data and inflationary theory were the only evidence for a vast, possibly infinite universe, the case would already be strong. But there is an independent line of evidence from the late universe. From observations not of the cosmic microwave background but of distant galaxies and supernovae, that reinforces and extends the picture. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, made an observation that upended cosmology. They were using Type 1a supernova as standard candles, sources of known luminosity that allow distance measurements, to map the expansion history of the universe. The expectation before the measurement was that the universe's expansion should be slowing down. Matter has gravity. Gravity attracts. A universe full of matter should be decelerating as gravity pulls everything back toward everything else. The measurement showed the opposite. The expansion of the universe is accelerating. Distant galaxies are receding faster than closer ones, not because they are moving away from us, but because the expansion of space between us and them is accelerating. The universe is not just expanding, it is expanding faster and faster. The cause of this acceleration is unknown. It is attributed to a term in Einstein's equations of general relativity called the cosmological constant, or to a more general class of energy called dark energy, a property of space itself that fills the universe uniformly and has a negative pressure that drives the expansion. Dark energy constitutes approximately 68% of the total energy density of the universe, as measured by Planck. The discovery of dark energy won the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. It is one of the best confirmed discoveries in modern cosmology. The accelerating expansion is detected in multiple independent datasets: supernova surveys, baryon acoustic oscillations, weak gravitational lensing, the CMB, all consistently. What does dark energy have to do with the infinite universe? Two things. First, dark energy is consistent with a flat universe. The specific value of the dark energy density, combined with the matter and dark matter densities, sums to the critical density. 2. The level of precision that Planck measured. Dark energy is part of what makes the universe flat. Remove dark energy from the budget, and the universe would have the wrong total density and would not be flat. Dark energy's existence is, in part, a consequence of the requirement of flatness, and it is confirmed by independent supernova and large-scale structure measurements. Second, and more profoundly, dark energy changes the fate of the universe in a way that makes the infinite universe's implications permanent rather than temporary. In a universe without dark energy, a matter-dominated flat universe, the expansion continues but decelerates. And in the very long run, gravitational attraction would eventually halt the expansion and, depending on the curvature, potentially reverse it. In a universe with dark energy, which is what we live in, the expansion accelerates without end. Every galaxy not gravitationally bound to our local group recedes faster and faster, eventually crossing the cosmic horizon and becoming invisible to us forever. The observable universe is shrinking, not in physical size. The 93 billion light-year sphere continues to grow as light from ever more distant regions has had time to reach us. But in terms of what it will eventually contain, galaxies that are currently visible will eventually recede beyond the horizon and become permanently inaccessible. In 1 trillion years, an observer in what is now the Milky Way will see only the galaxies of the local group, the Milky Way, Andromeda, and their smaller companions, against an otherwise dark sky, all other galaxies having receded beyond the horizon. This cosmic loneliness is the fate of an observer in an accelerating universe. But the universe itself, the total universe, beyond the observable horizon, does not shrink. The regions beyond the horizon continue to exist. Their galaxies continue to form stars and evolve. The distance between us and them grows, but they do not vanish. An infinite universe with dark energy is infinite at every moment of its future. The volume of total space grows without bound, forever, and the richness of cosmic structure beyond every horizon continues without limit. Chapter 8: The Hubble Tension. A crack in the picture. Before we reach the full implications of infinite cosmology, there is an honest anomaly that needs to be addressed. The evidence for a flat, dark energy-dominated, nearly infinite universe is strong. But within that framework, there is a persistent and growing discrepancy between two independent measurements of the universe's current expansion rate, the Hubble constant, that has not been resolved. This tension has been growing in statistical significance for the past decade, and at its current level, it cannot be dismissed as a coincidence. The Hubble constant, denoted h0, measures how fast the universe is expanding, specifically, how fast 2 points in space separated by a given distance are moving apart due to cosmic expansion. It is measured in kilometers per second per megaparsec. A higher Hubble constant means a faster expanding universe. A lower constant means a slower one. Two main methods exist for measuring h0, and they give different answers. The first method is the early universe measurement, using the CMB as measured by Planck, combined with the standard cosmological model, to extrapolate the expansion rate from the early universe to today. Planck gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec, with an uncertainty of about 0.5. The second method is the late universe measurement, using the cosmic distance ladder, a sequence of overlapping distance measurements that chain together from nearby Cepheid variable stars to Type 1a supernovae in distant galaxies to directly measure the current expansion rate. The most precise late universe measurement from Adam Rees and the Shoes collaboration gives a Hubble constant of approximately 73 kilometers per second per megaparsec, with an uncertainty of about 1. The discrepancy between 67.4 and 73 is about 5.5 kilometers per second per megaparsec. This sounds small, but the statistical significance of the discrepancy, given the quoted uncertainties, is approximately 5 sigma. A 5 sigma discrepancy in physics is the threshold conventionally used to declare a discovery. Here, it is the threshold of a problem. The Hubble tension means that either one or both of the measurements contains an unidentified systematic error, or the standard cosmological model. The flat, dark energy-dominated universe, with the parameters measured by Planck, is wrong in some way. Both possibilities are unsettling. If the standard model is wrong, the flatness result and the infinite universe implication might be affected. If there is a systematic error, the most precise measurement we have of the universe's geometry might be subtly off. The honest position is this: the Hubble tension is real, it is not explained, and it is large enough to take seriously. Dozens of papers have proposed explanations: early dark energy, additional light species, modified gravity, interacting dark matter, and none of them has achieved consensus. The tension may eventually resolve into a systematic error in one of the measurement chains, or it may resolve into new physics. At this point, nobody knows. The range of proposed new physics resolutions is instructive. Early dark energy models propose that there was an additional dark energy-like component in the early universe that briefly boosted the expansion rate before recombination, compressing the sound horizon and raising the CMB inferred Hubble constant toward the late universe value. These models can reduce the tension, but require introducing a new physical component with properties calibrated to make the numbers work. They have a somewhat fine-tuned character that makes physicists uneasy. Interacting dark matter models propose that dark matter had some coupling to radiation in the early universe beyond gravity, changing the acoustic dynamics and altering the CMB inferred Hubble constant. Modified gravity models propose that Einstein's general relativity needs a correction at cosmological scales. Additional light relativistic species, extra neutrino-like particles beyond the 3 known neutrino flavors, would change the expansion rate before recombination in a specific way. None of these explanations has become the consensus answer, partly because each introduces new problems alongside the one it solves. The systematic error possibility remains very much on the table. The distance ladder measurement chain, Cepheids to supernovae, has recently faced scrutiny from the James Webb Space Telescope, which has measured Cepheid distances in nearby galaxies with unprecedented precision. The JWST Cepheid measurements are consistent with the previous Hubble Space Telescope measurements, suggesting the Cepheid calibration is not the source of the error. This has actually sharpened the tension rather than resolving it, as one of the most suspected systematic error sources has been scrutinized and found clean. The most likely outcome, according to many cosmologists, is a combination of a small systematic error on one side and some new physics on the other. A messy resolution rather than a clean one. Whatever the resolution turns out to be, the flatness measurement is not implicated. What the Hubble tension does not do is overturn the flatness measurement or the evidence for inflation. The CMB measurements that give both the Hubble constant and the flatness are internally consistent. The tension is between the CMB inferred expansion rate and the directly measured one, not within the CMB data itself. The geometry of the universe, flat to within 0.4%, is not the parameter in tension. The Hubble tension is a discrepancy in the expansion rate, not in the curvature. So the Hubble tension is a genuine problem in cosmology, a puzzle that needs a resolution, a potential crack in the standard model. But it is not evidence that the universe is not flat. It is not evidence against an infinite universe. It is a measurement discrepancy that currently lacks an explanation, and that may eventually point to new physics, which could make the universe even stranger than the infinite flat model implies, not simpler. Chapter 9: Eternal Inflation's Full Implications. The Multiverse Beyond Infinity. In Part 1, we established the Level 1 multiverse. the idea that an infinite flat universe, filled with the same quantum mechanical density fluctuations in every direction, must contain infinite repetitions of every possible configuration of matter, including infinite copies of the observable universe, infinite copies of you. The level 1 multiverse is strange and difficult to absorb, but it is in some ways the most conservative of the multiverses implied by modern physics. It requires only one thing: that the universe is genuinely infinite, and that inflation produced a vast, flat, uniform space extending far beyond what we can see. Everything in the level 1 multiverse obeys the same laws of physics as we observe here, the same constants of nature, the same standard model of particle physics, the same strength of gravity. The repetitions are physical copies made of the same stuff, operating under the same rules. Eternal inflation implies something considerably more radical. Before going further, it is worth being precise about the distinction between the level 1 and level 2 multiverses, because they are often conflated, and the conflation makes the argument harder to follow. The level 1 multiverse is purely spatial. It is what you get from an infinite flat universe with quantum mechanical fluctuations. The same laws of physics everywhere, the same constants, the same standard model, but infinitely many regions, most of them forever beyond our horizon. The copies of you in the level 1 multiverse are made of the same kind of matter as you, governed by the same forces speaking somewhere, the same languages, having the same thoughts. They are you in the most physically meaningful sense, just located elsewhere in a space too large for light to have crossed. The level 2 multiverse is categorical. It is what you get if the different bubble universes produced by eternal inflation nucleate with different physical laws, different constants of nature, different particle content, different numbers of large spatial dimensions. A level 2 copy of you is not possible in any meaningful sense, because in most level 2 universes, the atoms that make up you cannot exist. The level 2 multiverse is not about copies of observers. It is about the landscape of possible physics, most of which produces no observers at all. These two multiverses have different evidential bases and different implications. The level 1 multiverse follows almost directly from the flatness measurement and inflation. The level 2 multiverse requires eternal inflation plus a landscape of vacua, the string landscape, which is more speculative. Both are consistent with current data, but the level 1 case is considerably stronger than the level 2 case, and conflating them leads to the impression that the whole multiverse idea rests on speculative string theory, which is not true of the level 1 version. In the eternal inflation picture, our universe is a bubble, a region that exited the inflationary phase and underwent a hot Big Bang. The surrounding space continues to inflate. New bubbles nucleate continuously, each one a new post-inflationary space-time, each one potentially a new universe. In most versions of eternal inflation, each bubble nucleates from a quantum fluctuation of the inflatant field, and the specific way the field settles into its low-energy state after. Nucleation determines the physical laws of that bubble, its vacuum state, its constants of nature, its particle content. This is the level 2 multiverse. Not just copies of our universe with the same laws, but an infinite ensemble of bubbles, each potentially with different physics. The number of possible vacuum states in string theory, the leading candidate for a fundamental unified theory of physics, is estimated at around 10 to the power of 500 to 10 to the power of 272,000. An incomprehensible number of possible configurations of the extra dimensions string theory requires, each configuration corresponding to a different set of effective low-energy physical laws. This landscape of vacua is sometimes called the string landscape. If eternal inflation is real and string theory is correct, then across the infinite set of bubble universes produced by eternal inflation, every vacuum state in the string landscape is realized, not once, but infinitely many times. What does that mean in practice? It means there are bubble universes where the fine structure constant, the number that determines the strength of electromagnetic interactions, is different from ours. Universes where the electron mass is different. Universes where the strong nuclear force is weaker and atomic nuclei are unstable. Universes where dark energy has a different value, and the universe either collapsed billions of years ago or expanded so fast that matter never had time to cluster into galaxies. Universes where the Higgs field settled at a different vacuum expectation value, changing every mass in the Standard Model simultaneously. To make this concrete, the fine structure constant, alpha, has a value of approximately 1/137. This dimensionless number governs how strongly charged particles interact with each other through electromagnetism. It determines the energy levels of atoms, the wavelengths of light emitted by hydrogen, the chemistry of every molecule, and the structure of DNA. If alpha were a few percent larger, the nuclear reactions that power stars would be altered, and stars would burn through their fuel far more quickly, possibly not giving planets enough time to develop complex life. If it were a few percent smaller, the chemistry of carbon, the element on which terrestrial life is based, would change in ways that might prevent the formation of complex organic molecules. The strong nuclear force is even more sensitive. The proton-to-neutron mass ratio, combined with the strong force's coupling constant, determines whether hydrogen is stable, whether deuterium can form, whether helium is produced in the Big Bang, whether carbon can be synthesized in stars. Fred Hoyle, in 1953, predicted the existence of an excited state of carbon, the Hoyle state, specifically because without it, stellar nucleosynthesis would not produce enough carbon for life to exist. The prediction was confirmed. The fine-tuning of nuclear physics for carbon production is real, measured, and well documented. In the string landscape, most vacua do not have the right nuclear force coupling for stable carbon. Ours does. The word fine-tuned is sometimes treated as a loaded term, implying design, implying purpose. In the multiverse context, it means something precise and non-theological. The region of parameter space consistent with complex chemistry and long-lived stars is small compared to the total parameter space of possible physics. In a single universe, this small region must be occupied by coincidence. In an infinite multiverse, every point in parameter space is occupied by some bubble universe, and observers necessarily find themselves in a bubble where the parameters allow observers. The fine-tuning is real. The explanation is anthropic selection across an infinite ensemble. Whether you find this explanation satisfying is a matter of scientific taste, but the logic is airtight if the ensemble exists. Most of these universes are, by the standards of our physics, hostile to any complex structure. A universe with a slightly stronger gravitational constant might have collapsed before stars could form. A universe with a slightly weaker strong force might not be able to form stable nuclei at all. The parameter space of possible physics is vast, and the region of that space that permits complex chemistry, stable stars, long-lived planets, and anything resembling life is a tiny island. Our universe sits in that island not because the laws were designed for us, but, in the anthropic view, because only universes in that island produce observers who can ask the question. This is the anthropic principle applied to the multiverse, and it remains one of the most contested ideas in theoretical physics. The argument is, we should not be surprised to find ourselves in a universe with fine-tuned constants, because only finely tuned universes produce beings who find themselves anywhere. The constants appear fine-tuned from the inside, because only inside a tuned universe can there be an inside at all. Whether the anthropic argument is satisfying or whether it represents a retreat from the scientific goal of explaining why the constants have the values they do is a debate that has occupied the best physicists for decades. Stephen Weinberg used the anthropic principle in 1987 to predict the value of the cosmological constant, the dark energy density, before it was measured, arguing that if too large, it would have prevented galaxy formation and no observers would exist to measure it. The measured value came in close to his predicted range. This is often cited as the anthropic principle's most striking success. But here is the thing. Whether you find the anthropic multiverse compelling or infuriating, the underlying physics that produces it, eternal inflation combined with the string landscape, is not a fringe idea. It is a mainstream theoretical framework supported by the best-tested theory of the early universe and the leading candidate for fundamental physics. It may be wrong. The string landscape may not be real. Eternal inflation may not be the correct model. But these are not the positions of cranks. They are the working assumptions of a significant fraction of the world's theoretical physicists, including the people who won Nobel Prizes for the discoveries that underpin them. If they are right, the universe is not merely infinite. It is infinite in an extraordinarily rich sense, infinite in space, infinite in time, infinite in the variety of physical laws realized. A structure so vast that every possible physical law is instantiated somewhere in it, infinitely many times, in an endless proliferation of bubble universes separated by inflating space that can never be crossed, that will expand forever, that will never run out of room for new bubbles to nucleate. This is not a small claim. It is the largest possible claim about the structure of reality. And the evidence that points toward it, the flatness of the CMB, the spectral index of the fluctuation spectrum, the constraints on primordial gravitational waves, is real, is precise, and is consistent with nothing else as cleanly. Chapter 10. The Boltzmann Brain. The most disturbing implication of all. In the 19th century, the physicist Ludwig Boltzmann made an observation that has haunted physics ever since. Boltzmann was working on the statistical mechanics of gases, the framework that explains thermodynamic behavior from the random motions of individual molecules. One of the things statistical mechanics explains is why entropy, disorder, tends to increase over time. In any large system, there are vastly more disordered configurations than ordered ones. A collection of gas molecules is far more likely to be spread uniformly through a container than to spontaneously concentrate in one corner. The reason hot objects cool and cold objects warm, the reason broken eggs do not spontaneously reassemble, the reason time has a direction is fundamentally that disordered states are overwhelmingly more probable than ordered ones. Boltzmann noticed a profound implication of this reasoning applied to the universe as a whole. If the universe is in a state of very high entropy, maximally disordered, which is the state it will eventually reach given enough time, then any ordered structure we observe is a statistical fluctuation, an improbably large fluctuation of the entropy downward from the maximum. Boltzmann wondered, given an infinite amount of time, in a universe of infinite extent, would we not expect to see such fluctuations? And if we would, then the question becomes, what is the most common way for an observer to come into existence as a statistical fluctuation? The answer is not a whole universe full of galaxies, stars, and planets. A whole universe of complex structure is an extraordinarily improbable fluctuation. The most probable fluctuation that produces an observer is the smallest fluctuation that produces an observer. A single brain with a set of apparent memories of a past that did not actually happen, spontaneously fluctuating into existence from the thermal noise of a high-entropy background, lasting just long enough to have a single moment of experience, and then dissolving back into chaos. This hypothetical entity is called a Boltzmann brain. In a sufficiently old universe, or crucially in an infinite universe, the probability of a Boltzmann brain fluctuating into existence somewhere is not zero. In a universe with a positive cosmological constant, like ours, the long-term future involves an eternally expanding de Sitter space with a fixed temperature set by the cosmological constant. The Hawking-Gibbons temperature, roughly 10 to the power of minus 30 Kelvin, barely above absolute zero, but not exactly zero. This is a thermal bath. Given infinite time, that thermal bath will produce fluctuations of arbitrarily large complexity, including fluctuations the size of brains. The disturbing implication is this: in an infinite universe with an eternally inflating background, the number of Boltzmann brains produced over infinite time may vastly outnumber the number of normal observers. Observers who came into existence through the ordinary thermodynamic processes of stellar formation, planetary cooling, and biological evolution. If Boltzmann brains are more numerous, then the typical observer in the infinite universe is a Boltzmann brain, not a normal observer. The typical observer is experiencing a single, fleeting moment of illusory consciousness, with false memories of a world that did not exist, with no reliable sensory input about the external world at all. How would you know if you were a Boltzmann brain? You would not. A Boltzmann brain, by construction, would have apparent memories of a past, apparent sensory experiences of an environment, apparent continuity of consciousness, all of them statistical, fluctuations of an underlying thermal background, none of them corresponding to actual external reality. Your memories of reading part 1 of this video might be false. Your memory of your entire life might be false. The apparent external world, the screen you are reading this on, the room around you, the people in your life, might all be the internal contents of a momentary fluctuation in a universe that is otherwise maximally disordered. This is the Boltzmann brain problem, and it is not a thought experiment that can be easily dismissed. It is a serious, published, actively debated problem in theoretical cosmology, discussed in papers by Andre Linde, Alan Guth, Don Page, Sean Carroll, and many others. The reason it is taken seriously is that it poses a genuine challenge to infinite cosmology. If an infinite universe necessarily produces more Boltzmann brains than normal observers, then the assumption that we are normal observers predicts that we should be Boltzmann brains, which is inconsistent with our apparent experience of being normal observers, which means either the infinite universe picture is wrong, or the counting of observers needs to be done differently, or the implication about Boltzmann brains is avoided by some mechanism. Before exploring the proposed resolutions, it is worth sitting with why the Boltzmann brain problem is specifically a problem for infinite cosmology and not just a curious philosophical footnote. In a finite universe with a finite future, a universe that will eventually end in a big crunch, or that will expand but on a finite timescale, Boltzmann brain production is limited by the total available time. A finite thermal bath running for a finite time produces a finite number of Boltzmann brains. Even if that number is astronomically large, it is still finite, and it can in principle be compared to the finite number of normal observers. The comparison might or might not favor normal observers, but it is at least mathematically well defined. In an infinite universe with an eternal de Sitter phase driven by dark energy, the comparison breaks down entirely. The thermal bath runs forever. The number of Boltzmann brains produced over infinite time is not just large, it is formally infinite. The number of normal observers produced in the finite habitable epoch of a given galaxy's stars is finite. Infinity divided by a finite number is still infinity. In any accounting that takes the infinite future seriously, Boltzmann brains dominate completely and overwhelmingly. This is sometimes called the Boltzmann brain catastrophe, and it is a genuine theoretical crisis for infinite, eternal cosmology. It does not mean the theory is wrong, but it means the theory, as usually formulated, predicts that we should be Boltzmann brains. And since we are evidently not Boltzmann brains, or at least have overwhelming experiential evidence to that effect, there is a tension between the theory and our self-observation. Either the theory needs modification, or the self-observation is wrong, or the accounting of observers needs to be done in a way that does not simply count total numbers across infinite time. Several mechanisms have been proposed to avoid the Boltzmann brain problem. One is that the universe is young enough, and the Boltzmann brain production rate low enough, that normal observers still outnumber Boltzmann brains in the current epoch. This is probably true at the current moment in cosmic history. The universe is only 13.8 billion years old, far too young for significant Boltzmann brain production, but breaks down in the infinite future, where the universe has had infinite time for thermal fluctuations. A second mechanism involves modifying the cosmological constant, or the structure of the long-term vacuum state, to prevent the de Sitter phase from persisting indefinitely. If the universe eventually undergoes a vacuum transition, if our current vacuum is metastable and eventually decays to a new vacuum state, then the de Sitter thermal bath is interrupted before it can produce large numbers of Boltzmann brains. The transition would destroy our universe, replacing it with a new vacuum with different physics. This is deeply unsettling in its own right, but it avoids the Boltzmann brain problem by not allowing the thermal bath to run forever. A third approach, developed by Sean Carroll and collaborators, involves arguing that the correct measure for counting observers in an eternal universe, the way to compare the number of Boltzmann brains to normal observers, requires careful treatment of the infinite time limit, and that when done correctly, normal observers always dominate, or at least are not overwhelmed. This is technically demanding and does not have consensus support. The Boltzmann brain problem does not refute the infinite universe, but it reveals something important. An infinite universe is not just bigger than a finite one. It is qualitatively different in ways that create deep conceptual puzzles. An infinite universe contains infinite observers. Comparing infinite numbers of different types of observers requires a measure, a way of assigning relative probabilities to different regions of the infinite space. And the measure problem in eternal inflation is currently unsolved. There is no agreed-upon way to assign probabilities in an eternal, infinite space-time. Different choices of measure give different answers to questions like, how likely is it for an observer to find themselves in a universe like ours? And are normal observers more common than Boltzmann brains? This is one of the genuine frontiers of theoretical cosmology. Not a solved problem. Not a problem with a clear path to solution. A fundamental difficulty in the foundations of infinite cosmology that prevents the theory from making sharp, quantitative predictions about the nature and frequency of observers. Chapter 11. The Fermi Paradox in an Infinite Universe. In 1950, during a lunch conversation at Los Alamos, the physicist Enrico Fermi posed a question that has been generating discussion ever since. If intelligent life is possible and the universe is old and vast, where is everybody? The Fermi paradox, the apparent conflict between the high estimated probability of extraterrestrial intelligence and the complete absence of any observed evidence of it, has a particular character in a finite universe. In a finite universe, the Fermi paradox is a question about whether we should expect to have been contacted or observed by alien civilizations, given the number of stars, the fraction that host planets, the fraction of those that might develop life, and the age of the galaxy. In an infinite universe, the Fermi paradox takes on an entirely different character. In an infinite universe, if the fraction of planets that develop intelligent life is any positive number, no matter how small, then the total number of intelligent civilizations is infinite. Not billions, not trillions, but literally infinite. And in an infinite universe, if even a small fraction of those civilizations develop the capacity for interstellar travel or communication, the total number of such civilizations is still infinite. The question, where is everybody, in an infinite universe has a specific answer. They are everywhere, infinitely many of them, in an infinite volume of space that also contains infinitely many uninhabited regions and infinitely many copies of every inhabited region. But the Fermi paradox persists in an infinite universe because the question is not about the total number of civilizations in all of space. It is about what we observe locally in the observable universe. And in the observable universe, a finite sphere of 93 billion light-years diameter containing an estimated 2 trillion galaxies, we have detected no confirmed signal, no unambiguous contact, no artifact of any other civilization. The standard Fermi paradox analysis applies to the observable universe as a finite region. Why, given the number of stars and planets and the age of the galaxy, do we not observe other civilizations? The answers, the zoo hypothesis, the great filter, the rare Earth hypothesis, the communication gap, are all the same in a finite or infinite universe when applied to the observable patch. But the infinite universe adds a specific dimension to the Fermi paradox that is rarely discussed: the problem of Fermi copies. If there are infinite copies of you in the infinite universe, then there are infinite copies of Earth, infinite copies of human civilization, and infinite copies of every question about extraterrestrial intelligence. In the infinite set of copies of Earth, some will have developed interstellar travel, some will have spread across their local galaxy, some will have transmitted signals. In an infinite universe, there are infinite civilizations at every possible stage of development, including civilizations that have solved every problem you can imagine, reached every scale you can imagine, and transmitted signals at every frequency across every reachable volume. None of them can reach us, not because they have not tried, but because the distances involved in the level 1 multiverse are so large. The nearest copy of Earth at roughly 10 to the power of 10 to the power of 123 meters, that no physical signal from any copy civilization, no matter how advanced, could reach another copy. The speed of light applies. The copies are causally disconnected. The infinite proliferation of civilizations in the infinite universe is entirely consistent with us observing nothing, because the horizon of observation is finite. This illustrates something important about infinite cosmology and the Fermi paradox. The infinite universe does not help with the local Fermi paradox. It does not explain why we observe no other civilizations within the observable universe. The full observable universe contains a finite number of stars and planets, and has a finite age, and within it, the Fermi question is as sharp as ever. The infinite extension beyond the horizon is irrelevant to local observations. What the infinite universe does is change the context for thinking about the rarity of life. In a finite universe, if intelligent life exists only on Earth, that is a statement about how rare life is. In an infinite universe, intelligent life is common, infinitely common, by definition, because every possible configuration is realized infinitely many times, including every configuration that contains observers. But the density of observers per unit volume, the number of civilizations per cubic light year, could still be extremely low, consistent with the Fermi observation. An infinite universe with a very low density of observers is infinite observers separated by very large empty spaces, with the nearest non-copy observer potentially billions of light years away, and the nearest identical copy at 10 to the power of 10 to the power of 123 meters. The Fermi paradox in the context of an infinite universe resolves into a question about density rather than existence. Life is not rare in the sense of possibly non-existent. Life is rare in the sense of very low density. The two are quite different, and infinite cosmology makes clear which question we are actually asking. This reframing has a specific implication for the great filter argument, one of the most discussed responses to the Fermi paradox. The great filter is the idea that somewhere in the sequence of steps from simple chemistry to spacefaring civilization, there is at least one step that is so improbable that almost no lineage completes it. The filter is great in the sense of severely reducing the probability. It filters out almost every candidate lineage before it reaches the stage of interstellar visibility. The crucial question about the great filter is whether it lies behind us or ahead of us. If the filter is behind us, if the improbable step was something in our past, like the emergence of eukaryotic cells, or sexual reproduction, or multicellular life, then we are among the rare survivors of a filter that eliminated almost every other lineage, and the absence of visible alien civilizations is explained because almost nothing else passed through. This version of the filter is, in a perverse way, reassuring. It means civilizations are rare, but those that exist are probably not about to be destroyed by a future filter. If the filter is ahead of us, if the improbable step is something we have not yet encountered, like some universal tendency for civilizations to destroy themselves at a certain level of technological development, then the silence of the cosmos is not explained by rarity of origin, but by brevity of visibility. Civilizations reach detectable status and then eliminate themselves, and we are not yet at the stage where we would be visible. This version is not reassuring. In an infinite universe, the great filter analysis does not change in its local application. Within the observable universe, the question of where the filter lies is the same, but it changes in one specific way. In an infinite universe, no filter is so great that it eliminates all lineages. If the filter reduces the probability of reaching interstellar civilization to 1 in 10 to the power of 100, the expected number of such civilizations in the observable universe is essentially 0, explaining the Fermi observation. But across the infinite universe, the expected total number of such civilizations is still infinite. A filter of any finite severity leaves an infinite number of survivors across infinite space. This means the great filter in an infinite universe is not an existential filter in the cosmic sense. It does not determine whether intelligent life exists, because intelligent life necessarily exists somewhere, infinitely often. It is a local density filter. It determines how common we are in our observable patch. The question of whether the filter lies ahead of us becomes, in an infinite universe, a question about whether we as a civilization will be among the survivors in this particular region of space, not a question about the ultimate fate of intelligence in the cosmos. Whether that reframing is comforting or merely abstract depends on how broadly you define your interests. Chapter 12. Can we ever know the observational limits of cosmology? Here is the most honest statement possible about the infinite universe. We cannot prove it. Not because the evidence is weak, the evidence is strong, convergent, and consistent. Not because the theory is vague. Inflation is a specific, mathematically precise framework with testable predictions, many of which have been confirmed. But because the infinite universe, by definition, extends beyond any horizon we can ever observe. No measurement, no matter how precise, can directly sample the universe beyond the cosmic horizon. We are confined to the observable sphere, and what lies beyond it is forever outside our direct reach. This is not a unique problem in science. The interior of black holes is also beyond our observational reach. The far side of the moon was unknown for most of human history. The deep interior of the sun cannot be directly observed. Science routinely makes confident inferences about inaccessible regions based on theory confirmed inaccessible ones. The confidence with which cosmologists assert the flatness of the total universe, and therefore its likely infinite extent, is the same kind of confidence. Theory confirmed by observation in accessible regions extended by inference to inaccessible ones. But the specific structure of the infinite universe argument has an unusual character. It is not just saying we infer that what we cannot see is similar to what we can. It is saying we infer that what we cannot see is infinite, and therefore contains every possible configuration of matter, and therefore contains copies of us, and therefore has specific implications for the nature of personal identity and the meaning of uniqueness. The chain of inference, while each step is supported, runs a long way from the data. The points in the chain where the argument is most secure are the flatness measurement and the existence of inflation. Both are very well confirmed. The point where the argument becomes more speculative is the extrapolation from inflation occurred to eternal inflation occurred. Inflation as a finite event, a period of rapid expansion that began and ended globally, is distinguishable from eternal inflation in some models. Whether inflation is genuinely eternal depends on details of the inflationary potential that are not yet fully constrained by data. The Planck constraints on the spectral index and tensor to scalar ratio are consistent with eternal inflation and actually favor the model, classes that produce it most naturally, but they do not directly confirm that inflation never fully ends. The strongest direct evidence for the universe extending beyond the observable horizon, beyond confirming flatness and inflation, would come from a detection of the specific statistical signature of bubble collisions in eternal inflation. In the eternal inflation picture, other bubble universes form near our bubble and occasionally collide with it. A collision between our bubble and a neighboring bubble would leave a specific circular imprint in the CMB, a disk of anomalous temperature and polarization corresponding to the collision event. These imprints have been searched for in the WMAP and Planck data. The searches have found no confirmed bubble collision signatures, placing constraints on the collision rate. The absence of detections is consistent with the collision rate being low, but does not rule out eternal inflation. Most models predict collision rates low, enough that detections are not expected in current data. Future CMB experiments, including ground-based experiments like the Simons Observatory and CMB-S4, which are currently being built or planned, will measure the CMB polarization with unprecedented sensitivity. The detection of primordial gravitational wave imprints in the B mode polarization spectrum would be direct evidence for inflation at high energies and would strongly constrain which inflationary models are viable, further tightening the case for or against eternal inflation. The James Webb Space Telescope is also contributing to the picture, not through CMB measurements, but through its unprecedented observations of the high redshift universe. The universe as it was in the first billion years after the Big Bang. JWST has discovered that galaxies formed earlier and more abundantly than standard models predicted, raising questions about whether the standard cosmological model needs revision at early times. These observations are not evidence against an infinite universe, but they are reminders that the standard model has tensions and open questions that could, in principle, alter the picture. The JWST galaxy formation puzzle is worth describing in more detail because it is the most active current challenge to standard cosmology. In the standard model, galaxies grow hierarchically, small structures forming first, then merging into larger ones over billions of years. The first galaxies should be small and irregular, forming slowly in the first few 100 million years. When JWST began observing, it found galaxies in the first 500 to 700 million years after the Big Bang that are unexpectedly massive, containing stars of a combined mass comparable to the Milky Way, which should not have been able to form so quickly under standard gravitational collapse timescales. Several explanations are on the table. One is that the initial mass function of early stars, the distribution of stellar masses when the first stars formed, was skewed toward very massive stars, which form faster and produce more light per unit mass, making early galaxies appear more massive than they are from their luminosity alone. Another is that feedback processes, the winds and radiation from early stars blowing material out of galaxies, were less efficient in the early universe, allowing faster accumulation of stellar mass. A third, more radical possibility is that some modification to the cosmological model is needed. Perhaps the initial power spectrum of density fluctuations differs from the standard prediction on small scales, producing more concentrated structures earlier. None of these explanations has achieved consensus. The JWST observations are relatively recent, and the field is still in the analysis phase. What is clear is that early galaxy formation is more efficient than standard models predicted, and understanding why will require either revised models of star formation and feedback physics or some modification to the underlying cosmological framework. If it turns out to require modifications to the inflation-produced power spectrum, to the same fluctuation spectrum whose spectral index Planck measured, it could in principle affect the precise relationship between inflationary theory and the observed universe. This is a live area of research, not a resolved question. JWST will continue observing the high redshift universe for years, building up a statistical sample of early galaxies, large enough to distinguish between the competing explanations. Whatever it finds, the results will refine our understanding of structure formation in an infinite universe, not undermine the fundamental case for that universe's infinite extent. The probability distribution for the total size of the universe, given current data, spans an enormous range. The universe could be 1,000 times larger than the observable universe, or 1,000,000,000,000 times, or 10 to the power of 10 to the power of 123 times. The data allows all of these and cannot distinguish among them because all of them are consistent with the flatness and inflation evidence. The one thing the data can begin to constrain is the lower bound. The universe must be at least significantly larger than the observable horizon, because the topological repetition searches have found no evidence of a closed topology within range. The exact size beyond that is observationally indeterminate. This indeterminacy is not comfortable for science, which prefers falsifiable predictions to unfalsifiable inferences about inaccessible regions. Some physicists, most prominently George Ellis and Joe Silk, have argued that the multiverse and eternal inflation cross a line from physics to metaphysics, because their central claims cannot in principle be directly tested. Their concern is methodological. If a theory makes claims about regions that can never be observed, is it science or cosmological theology? The response from the other side, from Tegmark, Guth, Lind, Vilenkin, is that testability is not the only scientific virtue, and that a theory's status as scientific depends on whether it makes testable predictions about accessible regions, not on whether all of its implications are directly testable. Inflation makes dozens of precise, confirmed predictions about the observable universe. The eternal inflation extension of inflation is the simplest, most natural extension of a confirmed theory. The fact that the extension implies claims about unobservable regions does not automatically make it unscientific. It makes it less directly testable, which is a different thing. This debate has not been resolved. It may never be resolved to everyone's satisfaction, but it is a genuine philosophical dispute about the scope and methods of science, not a disagreement about the data. The data points toward inflation. The most natural theoretical extension of inflation is eternal. The most natural outcome of eternal inflation is an infinite universe. Whether that chain of inference constitutes scientific knowledge, scientific hypothesis, or scientific speculation is a question about epistemology, not about physics. Conclusion: what it means to live in an infinite universe. Let's take stock of what the evidence actually says. The universe is flat to a precision of 0.4%, confirmed by multiple independent measurements using multiple independent methods. A flat universe is consistent with being infinite or with being a very large finite torus, but searches for topological signatures have found nothing within the observable horizon. The theory that best explains the flatness and simultaneously explains the smoothness of the CMB and the specific character of its fluctuation spectrum is inflation, which in its most natural and most data-consistent versions is eternal, producing an infinite universe. Dark energy confirms the flatness budget and implies the observable universe will spend eternity shrinking relative to the total, as the space beyond the horizon recedes forever. The Hubble tension is real but does not affect the flatness measurement. Taken together, this is evidence, not proof, but strong, convergent, multi-method evidence that the total universe is vastly, possibly infinitely, larger than what we can see. And if it is infinite, then we have established there are infinite copies of you, your specific history, your specific memories, your specific experience of this moment, all of them happening right now infinitely many times, at distances so large that no physical process could ever connect you to any copy. Causal disconnection does not make the copies less real. It makes them permanently unreachable. The question at the end of the intro, whether this is terrifying or liberating, turns out not to have a universal answer. The terrifying reading: you are not unique, not in any physical sense. Everything you have ever done, every thought you have ever had, every moment you have lived is being replicated infinitely, diluted into a statistical pattern across the universe. The sense of singular selfhood that feels like the most fundamental fact of your experience is not a fact about the universe. It is a consequence of the finite speed of light and the finite size of the observable horizon. Step outside that horizon and the singularity dissolves. The liberating reading: everything that has ever mattered to you, every experience you have valued, every person you have loved, is real. And real, moreover, in an unlimited way. The universe is not a place where the things you care about are rare accidents in a vast indifferent darkness. It is a place where every configuration of meaning and experience that can exist does exist infinitely many times. The love you feel is not a fragile flicker in an empty cosmos. It is one of the infinite instances of something that the universe, by its structure, inevitably produces. Neither reading is complete. Both are consequences of the same physics. The infinite universe does not care which reading you find more comfort in. It proceeds according to quantum mechanics and general relativity regardless of human preferences about its implications. There is, however, a practical question buried under the philosophical one. Does it change anything, knowing this? If you accept the evidence and the reasoning, if you grant that the universe is very likely infinite and that your physical configuration is repeated infinitely many times, does it change how you live, what you value, how you treat the people around you? The honest answer is probably not, and probably not because of a failure of imagination rather than a failure of relevance. The copies of you at 10 to the power of 10 to the power of 123 meters are not you in any experiential sense. You cannot communicate with them. You cannot coordinate with them. You cannot draw any comfort from their existence in the way you can. Draw comfort from a friend's sympathy or a colleague's shared effort. The causal disconnection is total. The copies are real in the physical sense and completely absent in the experiential sense. What the infinite universe does change is the frame. The question, does my life matter in the context of an infinite universe? Sounds like it should have a deflating answer. No. Obviously, you are one of infinitely many instances of an already negligibly small configuration of matter in an already vast observable universe. But the question contains a category error. Mattering is not a function of uniqueness. Mattering is a function of consequence, of what your actions cause, who you affect, what you build or destroy or sustain in the world you actually inhabit. An infinite universe does not dilute the causal consequences of your actions within your light cone. The person you help is helped. The person you harm is harmed. The work you do is done. These things are real within the observable universe regardless of what exists beyond it. The infinite universe is, in this sense, irrelevant to ethics, not because the physics is uncertain, but because ethics operates at the scale of causal reach, and the scale of causal reach for any individual or any civilization is the observable universe. What exists beyond the horizon neither adds to nor subtracts from the weight of any choice made within it. But it does change one thing about meaning: the question of cosmic loneliness. A finite universe, especially a universe that began at a specific moment, will end at a specific moment, and contains a finite and potentially small number of conscious beings, has a quality of fragility, of rarity, of significance from scarcity. Everything that exists in it is precious, partly because there is a limited supply. An infinite universe has no scarcity. Every configuration is realized infinitely many times. Preciousness from scarcity does not apply. If meaning requires scarcity, the infinite universe is a meaning-dissolving discovery. If meaning does not require scarcity, if what matters is the specific causal web of relationships and consequences you inhabit, not the frequency of your physical configuration across an inaccessible space, then the infinite universe changes nothing about meaning. Most people, when they think about it carefully, find that their sense of what matters is not, in fact, grounded in cosmic uniqueness. It is grounded in relationships, in projects, in the specific texture of the lives they are living. If that is right, the infinite universe is not a threat. It is simply a very large background against which the foreground of experience retains its full weight. What is clear is that the universe is far stranger than it looks. From inside the observable horizon, from the vantage point of a conscious being on a small planet around an unremarkable star, the universe looks like a dark, mostly empty sphere filled with distant lights. That sphere is real and it is enormous, but it is a fraction of a rounding error of the universe's actual extent. Beyond the horizon, more of the same. Galaxies, stars, planets, the same physics, the same quantum mechanical fluctuations evolving under gravity into the same structures. And in all that space, statistical inevitability doing what statistical inevitability does, realizing every possible configuration infinitely many times, in an endless proliferation of the same ordinary physics applied to an extraordinarily large canvas. The proof that the universe is infinite is not a single measurement. It is a convergence. The flatness of the CMB, the inflationary explanation for that flatness, the specific predictions of inflation confirmed in the fluctuation spectrum, the absence of any topological signature of a closed universe, the dark energy that completes the critical density and keeps the universe expanding forever. Each piece, individually, leaves room for doubt. Together, they constitute the strongest available argument for the most extreme claim about the structure of reality that physics has ever made. The universe is flat. It is probably infinite. It almost certainly contains copies of you. Your existence is real, and it is also one of infinitely many instances of itself. The physics points this way. The data supports it. The implications are genuinely, structurally, irreducibly strange. And in the face of all of that strangeness, the appropriate response is not panic and not dismissal. It is the same response that science has always recommended in the face of a universe larger and stranger than expected. Look again. Look more carefully. Keep measuring. The universe will not get smaller because we are frightened of how large it is. But it will get clearer and eventually more understandable, and possibly more beautiful the longer and more carefully we look. The universe is infinite, or close enough to make no difference. It contains everything that can exist, including somewhere the answer to every question we have not yet thought to ask.